really going to have output, let's look through this output and make sure that we can see what all of these values are. Okay, so if this is our analysis of the flight time versus drop height, the constant, that's talking about the y-intercept. So this is saying that the y-intercept is negative 0.03761. And this is talking about the slope. And so this right here is the slope that we're going to be writing in our equation. So if we wanted to write a least squares regression line for this data, then I could say that the flight time, and that would be in seconds. And what do I need on the top of this? I need a hat to show that I'm predicting, will equal negative 0.03761 plus the slope of 0.0057244 times the drop height, and that would be in centimeters. Now you might prefer to write this using y and x. So if you like that, y is the predicted flight time, again in seconds. X is the drop height that was actually done, and that is in centimeters. And so you could write this same equation using the hat. Y hat is equal to negative 0.03761 plus 0.0057244x. And so that could be another way you could write the exact same thing. So that's our equation. So let's see what other things we can get from this output. So from this output, interpret the slope of the regression line in context. Okay, so that's talking about as you increase your x, what does y do? So for every increase of 1 centimeter of drop height, the flight time of the helicopter is predicted, right, or estimated, or some word to show that you're just predicting it, will increase by 0.0057244 seconds. What is the real life meaning of the y-intercept? And if you think back to what the graph looked like, if we go back, I'm just going to go back these pages. If you think back, if you on this graph here, where would 0 be on this scale of, this would probably be about 100, this is 50. So like way over here, you can see that this is really extrapolation, and you're not going to have a negative flight time anyway. So going back to here where I'm going to write down that the y-intercept would mean, for a drop height of 0 centimeters, the helicopter would have a flight time of negative 0.03761 seconds. This is extrapolation and meaningless. So I would always start out with what it means, how it is at 0 for the x value, and then write that sentence and then think about what that sentence actually means. So in this case, it's meaningless because you can't really have a negative flight time. Okay, so then what is the estimate for the standard deviation of the standard deviation of the flight times about the true regression line for each x value? This is also the size of a typical prediction error if we use the least squared regression line to predict the flight times of the helicopter across the drop heights. So what this is talking about is your standard deviation of your residuals. How much are these flight times predicted to be varying? And so I got to look up here and find my standard deviation of my residuals, which is this number right here. That's the standard deviation of residuals. And what does it mean? It's how much your prediction is expected to be off from the observed. So, okay, so here we did look at the standard deviation of residuals, and that's S. So, and in this case, S was equal to 0.168181. What are the units of S? The residuals should match the units of Y. So that is going to be seconds, okay, because it's the units of Y. So on average, the model predicts residuals of flight times of 0.168181 seconds. So on average, our prediction is going to be off of the observed values by about 0.1681 seconds. Standard error of the slope. So that we're looking at the S sub B, sometimes sub B1, because for slope. And now we have to look on our output. Where would we find the standard error for the slope? Well, it would be next to the slope. So if you look right here, that right there, that's your standard error column, and we're going to look on the slope row. That is the standard error for the slope. What would be the units for slope and slope error? So 0.000218, and the units of slope would be seconds per centimeter. Okay, so that has to match the units for slope. So on average, our slope will vary by approximately 0.000218 centimeters per second in repeated trials. R squared. Okay, what is R squared? That means 92.2% of the variation in the predicted flight times is accounted for by the model of, if I'm going to use the word versus, I need to say the flight times first. Flight times versus drop height. If I used and, I can change the order. What is the strength and direction of this linear regression model? Well, although the output up here only showed R, squared. See, this is where I see the r squared right here. Remember, we're not using this adjusted r squared. We're not using that. So when I see that r squared, that actually can help me get the r. So I can take the square root of that. I have to put it in as a decimal when I do that. So r is going to be the square root of r squared. And so it's going to be the square root of 0.922. Now, this could have been a positive or a negative. You have to decide if positive or negative. And in this case, because slope is positive, it's positive for this model. In this model, then r equals positive. So we're going to just use the positive value, but you have to watch for if the slope was the negative value. So in my case here, r is equal to the square root of 0.922, which is 0.9602. So I would call this strength strong. Is strong, ST with r equal 0.9602 and positive direction. The only way to see the form is by graphing it, but you can definitely see the strength and direction from the r. Okay, and in the next video, I'll do some confidence intervals and some t-tests.